Thank you very much. First, I'd like to thank the organizers, Matthias, Volker, Igor, and Carsten, for inviting me and giving me this opportunity to talk. And from my affiliation, you might see that it might be the black sheep of this wonderful workshop, but the materials, I hope you find it is more familiar. So I'm going to talk about electronic structure for large systems. And first of all, the question is why we are interested in large systems from physics, chemistry, or materials perspective. I mean, there are numerous examples showing that we're interested in them. We can be interested in large molecules or just quantum dots, which can easily contain hundreds, thousands, or even more atoms. And we might be interested in complex solids. In the past week, you might have learned that in the how to deal with simple crystals such as BCC or FCC, and which has 2 or 4 or 8 atoms per unit cell. However, there could be some complicated unit cells. For example, this recently developed metal organic framework, or MOF, and which has a quite fascinating unit cell structure, which contains hundreds or even thousands of atoms just in one periodic cell. And the structure is really complicated. And you might be interested in surface effects, where you just add a few layers of the substrate, and that will give you, again, hundreds to thousands of atoms. You might be interested in disordered or amorphous systems. Oh. Hello?
Now?
Hello? This better?
Is the sound working upstairs?
But
Yeah,
can you hear? Or I can just speak louder. Seems not an enormously large auditorium. But the recording is working? Okay. Can you hear me? Okay. So you might be interested in amorphous systems. And actually, just before I came here, I was contacted by a company in the US called Corning, and they're interested in some ceramic. Oh, wow. Okay. So they're this Corning company, and they are interested in some ceramic type of materials, and they are interested in large-scale calculations. Not that we can necessarily help them. We're still figuring out the preliminary possibility of whether our algorithms could be useful. But the preliminary thing they sent us, already the smallest system is about 1,000 atom disordered or amorphous system, and the medium-range system is already like 10,000 atoms. And you might be interested in solid-liquid interfaces, for example, in batteries, this solid electrolyte interface, and where you have some graphite type of things on one side, you have some electrolyte on the other side, and this order can very easily go to 10,000 atoms. And last but not the least, I would like to say that, remember, classical molecular dynamics simulation involves already routinely millions of atoms to orders of billions of atoms. And so definitely there's things to be studied for large systems there. But why large systems are very difficult? And in the past week, you have, I look at the website, and so there have been wonderful slides and talks talking about how to do Kohn-Sham density functional theory type of calculations. And for most of the theories or methods that you would like to use to solve Kohn-Sham DFT, you essentially need to keep track of the Kohn-Sham orbitals or eigenfunctions. And these eigenfunctions are generally delocalized in the global domain. And what does it mean in practice when you want to store it? It means you want to store it using a matrix. And this matrix is of a size, I call it order n by order n. That is, when you have n atoms, then you have order n degrees of freedom. This degrees of freedom can be quite general. If you use plane waves, it could be the number of plane waves. If you use FHI-aims, and could be the number of atomic orbitals, and so on and so forth. But generally, when you have n atoms, at least you need a constant number of degrees of freedom per atom to resolve it, and therefore you get this order n. And this one is the number of Kohn-Sham orbitals, which is number of electrons, or number of electrons divided by 2, it depends on how you treat the spin. So this is the order n by order n dense matrix. And no matter what kind of method you do, in the end, you have to satisfy the orthonormality condition, which means at some step you have to orthogonalize this matrix and get this order n by order n matrix. If you use dense solver, such as ALPA, I mean, there are more complicated things going on. And if you use sparse solver, for example, Davis method, You don't necessarily need to do it at every step, but in the end, at least you need to do this. So just this step gives you order n cube scaling. And the cubic scaling means that if you double the system size, you actually nearly increase the cost by a factor of 10, which is more exactly a factor of 8, and so on and so forth. So the cost increases very quickly. So there could be a drastic difference of dealing with a system containing 1,000 atoms and dealing with 10,000 atoms. So there have been a lot of work in the community of physics, chemistry, and material science in the past 2 decades to reduce this cubic scaling, and most notably this linear scaling type of work. This talk is not about linear scaling, so therefore I only want to say that they are all based on some sort of a truncation. You can truncate the Kohn-Sham orbitals, rotate the Kohn-Sham orbitals or one-year functions. You can truncate the 1DM or the density matrix. They're all based on the so-called nearsightedness of electronic matters for gapped system, as coined by Walter Kohn in 1996. And there have been some wonderful reviews, one a little bit earlier and one more recent on the development of linear scaling methods in the past 2 decades or so. So all of these methods, they are applied to systems with band gaps, which means that they fundamentally fail or shouldn't be expected to work well when you apply them to systems without a gap, for example, metallic system. And what we're interested in is some methods that are beyond linear scaling methods that not necessarily or for sure won't achieve linear scaling. However, we would like to develop fast methods for general systems. And they are not based on the nearsightedness principle. And still, you can reduce either the asymptotic scaling or you can reduce largely the pre-constant. So this is just the example we did in the past few years, and we're saying that you could apply these new methods, and I'm going to talk about in a second, called PEXSI, and to solve systems with around 10,000 atoms, which includes large DNA calculation, which goes a few tens of thousands of atoms, can be used to study large-scale structure of graphene nanoflake, which is about 10,000 atoms, study different boundary effect, or studies the large-scale phosphorine nanoflake heterojunction as a new candidate for solar cell materials, which again contains about 10,000 atoms. So one more thing before we go on to how the methods work. I'm sure you have seen this in the past week about this choice of exchange correlation functional in Kohn-Sham DFT. This is called the Jacob's ladder or Purdue's ladder of exchange correlation functional. At the bottom is often called the Hartree Hill, or just Hartree's world. There's no exchange correlation. Chemical I mean, it's very far away from chemical accuracy. You have LDA, GGA, meta-GGA, and this lower RAM functionals. Then you have some hybrid functionals. You have beyond hybrid, RPA and MP2, and you have whatever things that's beyond. And in the end, you reach the chemical accuracy. And this ladder, I think, has been presented for sufficiently number of times in the community, so people tried all kinds of different innovative ways of presenting that, but in the end, they convey the same information. So here, I'm drawing a dashed line deliberately between the third and fourth rung of the functional. And that is because, although when you see there is always some sort of systematic but not necessarily monotonic improvement of the function accuracy of the functionals when you move up the ladder, but the mathematical structure of different levels of the functionals are actually very different. In particular, if you look at the first, second, and third rung, I mean, they can look quite different or very different code up, but they are mathematically roughly the same thing. And I will say them, they are called the exchange correlation functionals with semi-local structure. I will explain why is that. And then moving up to the hybrid functional, the mathematical structure changes drastically, and or in the math terminology, here you are dealing with a differential operator, and here you are dealing with an integral differential operator. And therefore, the cost has increased very drastically. And when you go to RPA, that becomes an even more different beast, and beyond, I don't know what that is. So the talk of this talk, I'm going to focus on up to hybrid functional. I won't be talking at all about RPA, and because I believe there are still many theoretical issues to be resolved there. More specifically, I'm going to talk about two things, if I had the time. And the first is about how to accelerate semi-local functional calculations. And as I said, in the end, what I'm dealing with is an operator that essentially looks like this. I have a Laplacian, and there could be some local, non-local pseudopotential, but that's fine. And then I have a VR, which is essentially a local or semi-local quantity. And for this, what I'm going to claim is it is possible to reduce the scaling for general systems from order n cubed to at most order n square. Okay, so you can actually achieve drastic reduction in terms of the complexity, but I would like to point out the caveat or the assumption for this to work right now, while you still remember, while this works for small basis set. By small basis set and sparse basis set, what I mean is atomic orbitals like the tier 1, tier 2 of FHIMs or siesta basis, type of basis, so on and so forth. Okay, definitely not applicable to plane waves where you have a dense matrix. I'll explain why this is. And the second one is a non-local hybrid functional. And this one would, compared to this, you just add one term. Roughly, I just put a VXRR prime here. But this VXRR prime is, represents an integral operator, and which drastically changes the mathematical structure and the possible things that you can do, and not least because it's dense. So because this is dense, and I want to say that it is in general, other than linear scaling, not possible to really achieve below order n cube scaling, unless you want to leave it with an enormous largely pre-constant. But still, one can do the cubic scaling method but drastically reduce the pre-constant. That is really blocking most of the people from doing hybrid functional calculations. And this one is applicable to large basis set, which means you can do it for very dense basis, atomic orbitals, but even more straightforwardly, let's say if we want to do plane wave calculations, and how do you accelerate that? For all the methods I'm going to talk about, there's no band gap assumption. So first, let me talk about semi-local functional. And now we go a little bit deeper into the mathematical structure of Kohn-Sham DFT. So I have skipped the Kohn-Sham equations I assume you have seen in the past week. But if you think about what is the Kohn-Sham equation doing, you have a row called the electron density, and you form the Hamiltonian. And once you form the Hamiltonian, you diagonalize it, or partially diagonalize that, and you get the Kohn-Sham orbitals. From the Kohn-Sham orbitals, you sum up the square of the norm of the Kohn-Sham orbitals at each point, and then you get a new electron density. Okay, it sounds like the standard procedure to do. But if you step back for 1 second, and you realize that the fact that you use the eigensolver is only a tool. Is not the definition of Kohn-Sham equations. Or what I'm saying is once you have your H constructed from whatever the previous row, and all you need to do is have some means to get you to the new electron density. Okay? And if you could use an eigensolver, which is the most standard way of doing that, but not necessarily the case. As long as you have some way of going from one density to another, you can continue your self-consistent loop. And this is exactly the point I'm going to talk about. If you look at, for example, let's say a gapped system, for instance, and you sum up the square of the norm of first n/2 orbitals, and first thing I do is to augment, so psi 1, psi 2, to all the way to psi n/2, and all the way to infinity, or nt, the dimension of your Hamiltonian after discretization. Here I'm assuming, for simplicity, I'm using orthogonal basis. So psi 1, psi 2, all the way to psi infinity, I just put them together, and then I put a diagonal matrix in the middle to be determined, and then I have a psi 1 to psi nt, and do the transpose of that. In order to achieve an equal sign here, all I need to do is to put a 2 for the first n/2 orbitals, or I choose a chemical potential mu such that for all the eigenvalues below mu, and I put the 2, and all the eigenvalues above mu, I put it to be 0. And then you just do the linear algebra, you realize it is exactly the same thing. However, here I'm going to introduce this chi, which is almost like a Heaviside function satisfying if it's below the chemical potential is 2, above chemical potential is 0. I can much simplify this representation by noticing that epsilon is the eigenvalue of a Hamiltonian, and the psi is the eigenvector of the same Hamiltonian. Then, going back to the knowledge of linear algebra, we know that this is actually the definition of a matrix function. So I'm going to write this chi not as a regular function, but as a matrix function. But then you realize that this is x and this is the same x. If they were y, then it would be the kernel or just the matrix function. But the fact that this is x and this is x coming from here, you pin x and y together. It means you're only interested in the diagonal of this matrix function. Or for insulating systems with a gap, I can just simplify the whole Kohn-Sham DFT using this one line, which is have a row, I get the h, I have to choose a mu, I evaluate this matrix function, extract its diagonal, I get a new row. Okay? The whole Kohn-Sham DFT can be written down in this one line if you have this, if you are interested in the row-to-row map. So what would you do for a non-gapped system? There are many ways to regularize that, and one of the most popular way, as pioneered by Mermin, is this Fermi operator formulation, where you have a nonlinear fixed point formulation. So instead of a diagonal function, you replace this by a Fermi-Dirac function, and together with a normalization condition so that you do know how to choose mu. And this is the picture of that. The black line is the Heaviside function or a step function. And in the case of finite temperature, I smear it a little bit and introduce a beta, and so it becomes a smeared version of that. And this beta has the physical interpretation of inverse temperature, but it is possible for you to exchange this to other favorite smearing, whatever the Gaussian smearing or this cold smearing whatsoever. They're the same thing. So then this means it is possible to solve Kohn-Sham DFT in principle without involving any eigenvalue or eigenfunction. So if I want to say take-home message, this is the one, which is the Kohn-Sham DFT. If you solve with eigensolver, it is possible, and maybe over 95% of the people do that. But there exists the possibility of solving this without writing down even any eigenvalue or eigenfunction. So this is precisely what we do, and which is, what if you can expand, instead of using the eigensolver, what if you can expand the Fermi-Dirac function using some simpler functions for which the diagonal you can directly evaluate without invoking the diagonalization procedure. And there are many ways of doing that, and with kind of different complexity. And one of the ways which we believe at least achieved for the first time the so-called logarithmic representability complexity, but it's not important here. So is the following. It's a very simple representation. So remember, before I would like to evaluate the diagonal of this complex thing. I mean, the exponential on the denominator acting on the matrix, not inverse, not exactly know what that means. But I can expand this function, which is a meromorphic function in the complex plane, into a set of functions with a simple pose. And if you learn your quantum many-body or condensed matter physics, you will realize that, well, the Fermi-Dirac, you can expand it using the so-called Matsubara type of representation, give you essentially represent the hyperbolic tangent with the infinite number of poles, and that is essentially how you use to evaluate many of the Green's function related quantities. But the number of Matsubara poles are very, very dense, and there are infinite of them. If you want to directly use it for numerical computation, it is a disaster. But it is possible to obtain a representation that is much, much, much more efficient than the straightforward Matsubara representation. And in particular, you can evaluate this thing using Green's function like quantities, where omega and z are just complex numbers, and the number of terms you need to resolve as to certain accuracy, let's call it epsilon, is only logarithm dependence on beta delta E, which is a dimensionless number characterizing the difficulty of expanding this function. So for the purpose of this talk, we can just think this rho, this Cone-Sham map I talked about, can be almost equivalently, and this error can be made arbitrarily small. You can almost equivalently represent that using this simple formula. And therefore, the only thing that you need to do is to figure out how to evaluate the diagonal of some inverse matrices of this form. And in particular, now comes why I assume the so-called semi-local functional. Because when you have a semi-local functional, you only have two paths. And one is a Laplacian operator, and the other is some non-local pseudopotential. Let's just forget about that. And then there's the exchange correlation, which again lies on the diagonal, very close to the diagonal, like a Laplacian operator. So therefore, after discretization, proper discretization, let's say atomic orbital, you will end up with a sparse matrix. We only need H to be sparse. So there is a big difference between assuming H is sparse and assuming the so-called nearsightedness. If H is sparse, what I'm just saying is you have a sparse operator or this differential operator, and you use a localized basis. I mean, you can even use finite element basis, it still gives you a sparse thing. But this corresponding density matrix, which is this without the diagonal, can be fully dense for the simple reason that if you have a sparse matrix, its inverse is in general not sparse, and you have to do some miracle like nearsightedness to make it sparse. So I'm not making any assumption of the sparsity of the inverse matrix. I'm only assuming the direct matrix is sparse. But if you think of this problem, now it becomes a linear algebra problem, which is you have a sparse matrix, and whether you can evaluate the diagonal of its inverse efficiently without really computing the whole inverse, because you compute the whole inverse, you again go back to the order n cube scaling. So this is the second piece that we came from, which is called selective inversion. Simply speaking, it is, looks complicated, but let me just explain it intuitively. It is just a fact in linear algebra. Just like when you do Gauss elimination, it is a fact. This is a fact of the same level. So the fact is the following. You have a sparse matrix, let's call it A, and for simplicity, let's even think it is symmetric. So A, for a symmetric matrix, if it's even positive definite, you can do the so-called Cholesky factorization, which is A equals to LL transpose. And if it is non-positive definite, you can do so-called generalized Cholesky factorization, which is LD L transpose, where D is a diagonal. So this is what we use, which is A equals to LD L transpose. If A is sparse, then the Cholesky factor, which is L, I mean D is just diagonal, is in general also sparse. And you can know how many sparse non-zero elements are there. So the selective inversion states the following fact. Instead of computing, if you want to compute all the entries A inverse ij, not a single entry, not all the entries either, but if you would like to compute a certain range of entries which corresponds to the sparsity pattern of the Cholesky factor, okay? It's some sort of non-physical thing, but algebraically it makes a lot of sense. In particular, all the diagonal entries fall in this category, and all the entries corresponds to Aij is non-zero in this set in general. So if you would like to compute this, this is a closed set. You don't need to use any entry outside this set to compute any entry in this set. So that is a drastic simplification. I mean, the proof is a little bit more time-consuming to present here, but I just want to convey the idea, which is if you want to evaluate A inverse restricted to some given set, you don't need to touch all the entries or solve the whole inverse. There is a smaller set that you can restrict all your computation to be in that set, and you won't be lose anything. So that is the basic of the so-called selective inversion. And more specifically, you can analyze the complexity of it. Apparently, the only thing that matters is the sparsity of the matrix, because it's a direct method. And so when I talk about 1D, 2D, 3D here, I'm only talking about topologically, which is roughly, it is like a 1D, which is a nanowire, or 2D, like a surface, or 3D system. Okay? For general systems, 1D systems, like a nanotube, and you can immediately show that the cost is order n, in general, period. Whether it has a gap or not, I mean, you have a carbon nanotube, very long, whether the gap closes, doesn't matter. It's always order n. And for 2D system, which is like a surface, you get order n 1.5. And for 3D system, you get order n squared. And therefore, the cost is at the most order n squared for general systems. And let me stress it again, that it only relies on the sparsity pattern H and L, and is not based on the nearsightedness or the band gap. Therefore, it is applicable to metallic systems as well as insulators. So this is, we call this method Poe expansion and selective inversion, or PEXSI. I demonstrated this to work for orthogonal basis, but it works equally well. And in fact, you don't need this orthonormalization process as typically done for polynomial things. It works exactly the same way for orthogonal and non-orthogonal basis. I talked about how to apply this to compute energies, but all the other quantities you care about for the semi-local functional calculations up to, like energy, free energy, force, density of states, local density of states, they can all be computed without using any eigenvalue or eigenfunction. And recently we developed some robust, even more robust way of finding the chemical potential for both metallic and band-gapped insulators. And also recently we have some developments that handles not only the gamma points but also the K points, at least in principle. So it allows massively parallelization. So if you do the standard Computational MDFT with iterative method, usually this thing scales to a few hundreds of processors if you use VASP or some other thing. Or if you want to solve the dense problem like using scalar pack or LPA, you can go to a few thousands of processors. PEXSI is much more scalable, can easily reach 10,000 processors, if not 100,000 processors. And the reason is the following. This Poe expansion, the selective inversion framework, naturally gives you a two-level parallelization. And on the Poe level, you have some, usually it's 40 to 80 poles. Now, recently we reduced that a little bit. So this 20 to 80 poles, you can easily parallelize them. They're embarrassingly parallelizable. These poles have nothing to do with each other than they share the same Hamiltonian and overlap matrices. And so there's an embarrassing parallelization level. And within each pole, you have a linear algebra problem. And you can do this selective inversion procedure in parallel as well. You can do that sequentially with one call. You can do that with OpenMP parallelization, which is under development. But you can do the MPI level parallelization up to, so far, about 6,000 processors MPI for one pole. You multiply this together, immediately get the 100K calls. But in practice, we routinely use 10,000 calls on the nearest computer available at LBL. And so this is, if you're interested in the algorithmic structure, you can, I recommend you to read this paper. And it is available online. And this PEXSI package, just at this website, distributed on the BSD license and has been integrated into a few codes, big DFT. Oh, I haven't updated that to FHR AIMS yet, but it is in FHR AIMS. But it is in FHR AIMS through this very recent electronic structure infrastructure project that currently is ongoing work with Volker and sitting in the audience and Jianfeng Lu at the Duke University. And I'm going to talk briefly about that as well. And so it is, you should just think it is a linear algebra routine, just like a scalar pack. The input is your Hamiltonian overlap matrices distributed in some format. And then it spells out the output, which is the density matrix or energy density matrix, which is the Poulet force, which can be used to construct the Poulet force in atomic orbital calculations. You don't need that if you use the orthogonal basis, or the free energy density matrix, which is used to compute the entropic term. And so this was a little bit of a 0.10.1. Has been under development for a few years, and this website is just written. I mean, I started doing this with some kind of a Doxygen stuff, and recently we finally are ready to release this kind of 1.0 with several new things added there, and to make ease of for the users to do that as well, and reduce the number of parameters. Also would like to make the website a little bit better. And so this one is to be released I think in the next month or so. So I said there's this LC project, and together with Volker and Jim Feng, and I think throughout the hands-on workshop, and you will also hear about this, but the basic I want to say is not only it includes PEXSI, but allows many other solvers such as LPA, LibOMM, Chess, and many others along the way, so that you can plug in as an electronic structure software developer. You don't need to go after one method after another and deal with interfaces, so on and so forth. You only need to pay attention to this one interface, and then it will automatically or semi-automatically enable you to have access to all these other methods. And our team implemented in our homebrew package DGDFT, and Volker done that in FHI, and it was actually rather easy to do. I highly recommend it. So also, this is an example of how to use the so-called LC-PEXSI interface, which is a PEXSI enabled through LC. And in FHI AIMS package, you should be now very familiar with this software now. And courtesy of Victor Yu from Duke University in Volker's group. And he has significantly simplified the interface so that in principle, if you are the user and would like to deal with the calculation using PEXSI with the default parameter, all you need to do is these three lines in the control.in, and you specify your KS method to be LC, LC method to be DM, stands for density matrix. It means you are directly computing the density matrix without having access to any eigenvalue and eigenfunction. Let me say it again. It's a while ago that the moment you touch the Kohn-Sham orbitals, that is order n cube, period. So the only way to reduce the order n cube complexity is don't touch it ever. So this is the DM, and then you choose the LC solver to be PEXSI. I don't guarantee whatsoever that this setup will immediately give you the speed up, and from our experiences, you do need to kind of know what you're doing, but I will be definitely very happy for discussion. I mean, for your system, whether this method is should be expected to give you benefit or not. But in principle, it should just work for all the systems. And these are a bunch of test systems. Let me see, how am I doing on time? So I have 20 minutes or so?
No,
10 minutes.
As we would like to have this.
Okay, so let me skip a bunch of applications just to say that we could do it. Okay, yeah, so because I have a whole other topic haven't talked about yet. So you can do the density of states essentially on top, and the energy error is like 10 to the minus 8 to 10 to the minus 6 eV per atom, so it is highly accurate for both the energy and the force. You can achieve a drastic speed up, and this is PEXSI, this is scalar pack, this is done a few years ago, joined with Alberto Garcia, Georg Hughes, and I think in the audience, and Chao Yang LBL for 1D, 2D, 3D systems. Some applications, some other application. Okay, so. Yeah, the slides will be uploaded online if you're interested, and yeah, let me quickly summarize, and which is you can do the it's possible to reduce the complexity of a Computational DFT, but given that what you are dealing with in terms of the level of the exchange correlation functional, let me mark again that local basis on a small basis set is important, and also you should be expecting a slowdown when you use a large basis set, and that is because the scaling with respect to the basis set basis functions per atom is still cubic. And why? It is because still inverting matrices, there's a sparsity on the global level, but locally, if you give me a large basis, let's say doing a QZP basis functions, I mean, you just throw a lot of degrees of freedom that are densely interacting with each other locally. There's nothing you can do there. So the scaling with respect to the basis functions per atom, so that is still cubic. I don't want to mislead you on that. It's just with respect to the system size, it can be reduced. And you can do massively parallelization if you want to try the code separately. Or for example, we already have multiple requests actually and applications of this method. I didn't plug it in, so that's a little bit dangerous. So, okay, anyway. So the multiple requests of using PEXSI just to do some select inversion, not for electron structure, but for many other things like a QCD or even uncertainty quantification, Boltzmann equations. If you just want to use it for that, that would work perfectly well. And there are few implementations of it, but now I recommend that just using it through the LC. So in the next 10 minutes or so, let me try to talk about the different topic, which is hybrid functional, because I do want to get to that. And well, for this audience, I probably don't need to say why hybrid functionals is very, very important, and which is the yields significantly improved the description of a large number of properties, band gaps, localization, absorption, defect formation, so on and so forth. And just in 2017, there have been 2 papers, and one in PNAS, one in Science. Some of them might be controversial, but that's another thing. And basically saying that the hybrid functionals allows you to get systematically improved accuracy at a more quantitative level, both for understanding the band gap and for understanding the accuracy of approximating not only the energy, but also the density. And if you're interested, I highly recommend reading these papers. And mathematically, what it says is you just, instead of the normal PBE or blip functional that you're using, you mix it with a fraction of a new guy. And this is the term that is familiar from the Hartree-Fock thing. For example, if you use this PBE0 functional, what you're doing is to mix this functional with a fraction of the whole exchange operator. Or if you want to use the HSE, the screen exchange functional, you also add this thing. However, you slightly tune the kernel, not the bare Coulomb kernel, but the EarthC, so that you have a little bit more screening. And there are many other versions for the hybrid functionals as well. So the main feature is that the exchange operator now depends not only on the density, but also the density matrix. Actually, it makes the very argument I said before fail, which is for semi-local functionals, all you need to do is to have a map from row to row. That seems to be, I mean, really the bare minimum of everything I was talking about. However, even this bare minimum fails when you deal with hybrid functionals, because if you just have a row, you just have no way of defining this guy. You need the density matrix. Okay, so it means we have to rethink how we actually do deal with algorithms when we deal with this hybrid functionals. So in the end, it doesn't give you Computational-like equations, more like Hartree-Fock-like equations, and you need to do the self-consistent solution not on rho, but on the density matrix P or all the orbitals. You cannot avoid it. And for large basis set, one like plane waves, and one characterizing feature of the hybrid functional calculation is applying the exchange operator to vectors is very expensive.
it takes over 90% of the time, 95% of the time, or even more of the computational time just to apply these operators to vectors. And the typical way is you solve Poisson-like equations, and in the iterative method, you do it again and again and again. So let me say again, what does large basis set means in this particular context here? What I mean is the basis set is very large, and they have a large matrix. You just cannot diagonalize anymore. Or if you could diagonalize, it's a different story. But if you cannot diagonalize anymore, which is like plane waves, you must use an iterative method. And I want to say there, both the Coulomb and the Fock exchange, when you use the iterative methods, it scales cubically instead of quartically, like when you want to construct the two-center integral. And the Fock exchange term, however, has a very large pre-constant. That makes the calculation of a GGA, the high PB0 calculation, can be 20 to 100 times more expensive than the GGA calculation. So what we want to do is to reduce that, and at least at the beginning, without sacrificing the accuracy yet. So let me say why the hybrid functional calculation is so expensive. And that is because if you look at the algorithmic structure, for example, quantum espresso. Am I allowed to talk about quantum espresso here? Okay. So, okay, so good. So for example, quantum espresso, and this is minus Laplacian. You have some external potential, and you have the Hartree plus exchange correlation, and you have the exchange operator here. And the algorithmic structure looks a little bit funny if you look at the beginning. There's outer iteration, which does self-consistent iteration on P, the density matrix. There's the inner iteration that is split from the outer one that does self-consistent iteration on rho, the density, which is the diagonal of it. And why do you want to split? Is because if you merge them, you just have like a Rosen's equation, you will blow up immediately. And then you have an iterative method for the linear eigenvalue problem by fixing all these operators. And then you still use some iterative methods like a Davidson method to solve it, like or CG. And in this innermost thing, every time you do the matrix vector multiplication, you need to apply the hybrid functional operator, this Vx, to all the occupied orbitals. And this is very expensive, as I said. So that means every matrix vector multiplication involves solving order NE square Poisson-like equations. And it really overshadows everything that you're talking about. So, so adding this one operator, I want to say it really introduces three kind of orthogonal problems to your algorithm compared to a GGA calculation. The first is that the exchange operator is kind of small. In terms of the energy, which is 5% of the energy or so, but it's applied very frequently. And the second is each application is very expensive. And the third is because of this two-level SCF structure, it induces a very large number of SCF iterations. It's hard to mix a density matrix. So our approach is, probably I can only say it briefly, I was over-ambitious when I write the slides, and we developed something called the adaptively compressed exchange to solve the first problem. It can drastically reduce the frequency for which you need to apply the operator. And we recently developed something called interpolative separable density fitting, a new method in the context of density fitting to accelerate the exchange. And finally, there is some very recent work called the projected commutator DIS to really reduce the problem due to this two-level SCF thing. So let me skip something. I mean, previously there are a number of works along directions, but I want to say that if you look at the quantum espresso, for example, they were not implemented and so not commonly adopted, and some of them are system dependent. So our goal is not to get some linear scaling methods, but really a so-called non-linear scaling type of methods, but reduce the largely reduce the pre-constant. And here and there is really because when you add this one term, it introduces difficulties in many places in the algorithmic structure. But in the end, what we want to achieve is the cost of hybrid functional calculations to be a little bit larger. There's never going to be smaller, but a little bit larger, like factor 2 or 3 times larger than the GGA calculation, instead of 100 times more. And we hope the method is applicable to insulating and metallic systems. And some of the methods, like adaptively compressed exchange, is already available in packages like Quantum Espresso, and you can download that online from version 6.0 or so, and it's already implemented there. And the newer methods, we're still thinking about that. So how much time do I have? 4 minutes. Okay, let me just say the very brief idea of one thing, which is this adaptively compressed exchange. But hopefully it gives you some way of thinking about, there might be some new possibilities to do for this old problem. And this is, you have an operator, this exchange operator. And if you look at that, it's pretty nasty in 2 ways. On one hand, it is a dense operator, which means if you just truncate it somewhere, especially for small gapped system, it just doesn't work. For large gapped system, it works very well. And the second is a full rank operator, which means if you apply an SVD to it, it won't work very well either. So it's a dense and full rank. What are you going to do with this kind of operators from a linear algebra perspective? Actually, you could do something. And this is because although the singular values of Vx it decays very slowly, and however, when you apply a low rank approximation based on, let's say, singular value decomposition, what you're saying is essentially saying that the Vx minus is some approximation small for any function. But this is not what you need. What you actually need is Vx minus some approximation is small when applied to any occupied orbital, which is a physical number. It's not any orbital. Okay? So that is the core thing of this whole method, which is you have some operator, it's dense and full rank. And the compression doesn't come from the operator itself. The availability of a compression comes from that you don't care the operator applied to most of the orbitals. You only care the operator applied to some of the orbitals. And this is where the so-called adaptively compressed exchange comes from. In the end, it is, from implementation perspective, it's just very simple. It says that if you just do your normal exchange operator and you construct a sound matrix which is like overlap matrix, you do a Cholesky factorization, and then you multiply the resulting Cholesky factor to something you have computed, then you end up with this form that looks like a non-local pseudopotential and is going to be guaranteed to work almost the same way as you are doing with the full exchange at the level of convergence. As a matter of fact, at convergence, there's no approximation at all. And you can read this paper if you're interested in the more details. And it makes the application of the exchange operator to be much easier. It still needs to update it from time to time, but you only need to use a gem instead of solving these complicated Poisson-like equations. More specifically, what you do there is basically to remove the need of applying the full exchange from the innermost thing to the outermost thing. And you only updated that from time to time. There's no loss of accuracy, and there's no band gap assumption. So it has been implemented in a few packages. Quantum Espresso, in LBL, there's code called PTOAD. There's in progress with NWChem and also our own code. We have used that to do large-scale hybrid functional calculations in a plane wave basis for up to 4,000 atoms. And if you can look at the gap, band gap, and Hartree-Fock energy, it's almost on top of each other. We can do converged HSE calculation for 1,000 atoms from the top to the beginning within half an hour. And now, with some new developments, we can reduce that to 10 minutes. You can scale that reasonably well to a few thousand cores. You can some applications to water absorption on silicon, And recently, I don't have time to talk about that, which is how to further reduce the time with this AC ISDF. You see, at the beginning, at each outer SAF, you need about 1,000 seconds, even when you use already 2,000 processors per outer SAF, which is about 1,000 seconds. Now it is kind of reduced to 20. You can do the defect calculations in large-scale citizens, and at the level of hybrid functional calculations, as expected, there is a big difference in terms of the band gap for the systems with the vacancy and predicted by GGA and HSE. And more recently, we have been developing some new methods that allows you to do ab initio MD for the for hybrid functional calculations with large bases like plane waves. And this is some preliminary data obtained a few days, not long ago, about a 1,000 atom system. And you can do the MD, and the number of SCFs are much reduced compared to before, like 6 or so, and the drift is very small. So the summary of this part is basically to say that, well, for the adaptively compressed exchange, it is I went through that very quickly, but it is possible to reduce this cost, even though it sounds like a very old problem. And our goal is really to make the hybrid functionals no longer that much more expensive compared to GGA. And finally, I'd like to thank my collaborators, and I talked about a number of things, and I couldn't do this without help from many people, and in particular from Dr. Wei Hu, Dr. Wei Lejia, and Dr. Matthias Jacqueline from LBL, and many other people like Victor Yu and Joe Hughes sitting in the audience. And these are my senior collaborators, and I'd like to thank the funding, and thank you very much for your attention.